Okay, we good now? Everyone can see the screen?
Yeah.
Okay, wonderful. So thanks very much, everyone, for having me. And I'm going to be talking about some work on unclonable encryption, in particular, some constructions, and I'm hoping we'll get to the kind of connection with black hole physics. And this is joint work with Alex Poremba and Vinod Vaikuntanathan, who are both at MIT. Okay, so I guess we're kind of nearing an era, or maybe we're at least a couple of decades away from an era where potentially, quantum computers are a part of our world. Like we have access to quantum computers, maybe big tech has access to quantum computers, whatever. We're going to be in a quantum world, and the question I kind of want to foreground this talk with is, what would the cryptographic and security landscape look like in a quantum world? And I think what's most commonly popularized is the threat. So in particular, one popular thing that's considered is the threat that poses for RSA public key cryptography. So the setting here is that Alice is going to send some message to Bob, but she's going to encrypt it. So the way this is going to happen is Bob is going to put out a public key that's some large integer n, and Bob's going to keep the factorization of n to himself. So Alice can somehow use this public key to encrypt a message, send it to Bob, and Bob can use his secret key to decrypt and find out what Alice's message was. But any eavesdropper who's sitting in the middle, shouldn't have any idea looking at the public key and the ciphertext what's going on. Okay, and it turns out, thanks to Shor's algorithm, that this is completely broken if the eavesdropper happened to have a large quantum computer. And the reason for this is they can run Shor's factoring algorithm. So given n the public key, they can break it down into its factors, and then they have the secret key. And that's game over. They can decrypt just as easily as Bob. So a really important kind of field that a field of cryptography and its connection with quantum is post-quantum cryptography, which is basically how do we resist this threat exactly? So if Alice and Bob don't have quantum computers, but say we're worried about malicious eavesdroppers having quantum computers, is there still a way for Alice and Bob to do whatever they want securely, even if the eavesdropper happens to have a quantum computer? So this is a really important research area, but this is not what I'm going to be talking about in this talk. I'm just presenting it for contrast. What we're going to think about is quantum cryptography, which I think of as the hope. So there's new hopes for cryptography in a quantum world. And the idea now is let's also give Alice and Bob quantum computers. And now, is it possible that once we give the good guys quantum computers as well, is it possible then that we can realize secure functionality that was completely impossible classically? And we've known for some decades now that the answer is yes on a variety of axes. And one of these most relevant to what I was just saying is an observation, a work by Bennett and Brassard in 1984 that basically says yes. So for example, Alice and Bob, if they have quantum computers, can securely agree on a quantum secret key, even if Eve is eavesdropping. And moreover, let's even give Eve unbounded computational power. They can still make this happen. And this is very different to what happens in the classical world, right? Because in the classical world, if you want secure key exchange, you're going to have to assume that your eavesdropper is computationally bounded and that P is not equal to NP. We don't have to do any of that in the quantum world. So somehow, there's also hope for new secure functionality in a quantum world. And that's kind of what I want to focus around on this talk. And I would say kind of the central reason that there is this hope is the quantum no cloning theorem. So let me dive into what that is. So this was an observation we've known since the 80s. And what it informally says is that quantum information can't be copied and pasted. If I give you some quantum state, which is what this funky expression on the left is, there's no way for a quantum computer to take that state and spit out two different copies of that same state. And this is completely in contrast to the classical case, right? If I give you some classical string, there's nothing stopping you from copy pasting it and producing two copies. But quantumly, somehow it's baked into quantum mechanics that you can't do this. And basically, unclonable cryptography is leveraging this. We even have a robust variant due to Werner, which is that it's not even possible to generate something close to two copies of psi. Let me not specify exactly what I mean by close. And what I would argue is that it provides a hope for unclonable cryptography, because now you could hope for applications where what we want to safeguard against is the duplication of information. So in a classical world, this is completely off the table. In a
So
quantum world, thanks to no cloning, we can at least hope for it. Was there a question?
yeah, one question real quick.
Yeah.
So is it like I don't remember the quantum key exchange protocol.
Uh-huh.
Does that depend on no cloning, or I think doesn't it depend on something else, like more like teleportation or something? Like
Yeah, yeah, yeah. So I'm lying a little bit. Like there are
they're a
like
little
another thing it depends on is what you can think of as like an uncertainty principle. But kind of no cloning is certainly a necessary condition for it to work.
okay. Were you
Yeah,
saying
it's
something?
related. If you were able to perfectly clone the messages, then you could learn everything perfectly,
I see.
right? And then it would essentially be the same as classical.
Okay. Okay. Cool. Yeah.
Yeah. Okay, good question. And yeah, keep the questions coming. Um, okay, good. So the no cloning theorem basically provides us a hope for unclonable cryptography. But I'd like to make the case to you that it's rarely sufficient. We usually need something that's a lot stronger than a no cloning theorem to get like some kind of unclonable functionality. And so the way I like to think of this is kind of useful no cloning theorems. And this is a notion that's even stronger than the robust variant that we have thanks to Werner. And what I mean by this is that it shouldn't even be possible for both states to have some property in common with the original state. And I'm being intentionally vague about what some property means because that's going to be sensitive to the particular application. So the application I'm going to think about in this talk is secret key encryption. The unclonable variant of this was something that was formulated by Broadbent and Lord in 2020. So let me kind of step through this security setup step by step. So what you should imagine is that we have Alice on the left over here, who is the only honest party out of the four people in this picture. And she's going to sample a secret key theta, and she's going to sample a classical message X. And then for now, let's say uniformly. And now what she does is she encrypts her message under this secret key and sends it over to a cloning adversary who we're going to call Clarence throughout this talk. And now Clarence is basically going to attempt to clone this state. Obviously, like he's not going to succeed, but he can do something. And at the end, he has to kind of come up with two states and send them to two other adversaries, P1 and P2. And P1 and P2 don't get to talk to each other. They're in separate rooms or something like that. And later, the thing that Atlas might worry about is that later, maybe there's some security breach or something like that, and her secret key theta gets leaked. But now what we'd like to ensure is that even if P1 and P2 both have theta, they can't recover X. So the way this is formalized is that P1 and P2 both get access to theta, and then they output guesses for X. And they're going to win if both their guesses are correct. And I want to emphasize that, if the encryption was a classical string, this is completely impossible because Clarence could just copy paste whatever Alice sent him, send one copy to P1 and one copy to P2. So we're really relying in a crucial way on unclonability here. Okay, so this is kind of the basic setup this is kind of the basic setup for the whole talk. So I'll stop here if there are questions.
Makes sense, right? So one of them can guess it very easily, but both is the hard part.
Yeah, exactly. Yeah, so I'll point that out in a bit. But yeah, you're right. The challenge is getting both of them to guess it. Yeah. Good. More questions?
I'd also like to note for people that it's actually very important that they're getting the same key. If they get different keys potentially, then we actually know how to solve this. But as long as they're getting the same key on both sides, this is still no.
Yes. Yeah. Thanks,
So
Justin.
the problem, like, what do you mean?
Like we still don't know how to solve this outside of the random walk.
I see. So this paper doesn't solve this problem.
No, we don't. And I'll get into like exactly what we solve and what we don't a bit later.
Sounds good.
Good. Okay, and so let me kind of cut back to this notion I stated earlier in this talk about useful no cloning. So what I mean by that is that it shouldn't be possible for Clarence to produce any two states that reveal X, given knowledge of theta. It's not just that we want to prevent Clarence from cloning enc theta of X. We also don't want Clarence to produce any two states that are going to be sufficient for the parties to learn X. So this is what I mean. The kind of thing we're trying to shoot for here is much stronger than no cloning.
Wait, does the message need to be longer than a bit, or it just it's just a bit fine?
So I'll get there in a second. So if in the setup where the message is a bit, like that's kind of in the setting where like you only need to learn one bit, that's kind of where the open problems kick in. Like we're kind of able to prove more things if we can kind of consider the search setting and the message as long. But we'll get that.
So is it important that both the key and the message are classical?
I think for the purposes of this talk, yes. I mean, there are papers that kind of show interesting things by making the key quantum. But I think for at least for the scope of this talk, let's think classical messages.
Okay. In general, in quantum encryption, if the key is quantum, does it also need to be like lambda qubits, or is one qubit just enough since it actually does have like a lot of information? I'm not too sure.
Well, it does most likely need to be like lambda qubits unless you're doing something information theoretic. In which case, of course, you're limited to same size. But the reason is that you can only get so much information out of a
Okay, only so much
quantum
classical
state.
information.
Yeah, and
But
the
if you're
other-
like maybe encrypting quantum information,
well, the other thing is that if it's a short key, then you can guess a state that's close enough to
Okay.
this state that it will still decrypt with some probability. But if the state is long enough, there's an exponential drop off
Sure.
in guessing it.
just turn off them. Okay, sounds good.
Okay, excellent. More questions? Okay, in that case, I'll move along. So with that, let me kind of cut across to kind of more precise definitions in our results. So the kind of game I pitched to you a couple of slides ago and what I'm going to be thinking about in this talk is search security. So this is where, let's think of the message X as being a uniformly random bit string. And P1 and P2's goal is to just decrypt and actually recover this message in its entirety. So this is kind of what we denote as a security failure. And the value of this game is the probability over theta and the message that both adversaries guess correctly. And in search security, yeah, you would like this to be negligible in lambda. But I would contend that this is not the ideal notion, right? When we think about what we want for, a classical secret key encryption, we would like a notion of indistinguishable security. And so this is kind of the stronger game where like effectively all that's being encrypted is a bit, kind of throwing back to Matan's question. So what should happen here? So it's a chosen plaintext game. So the adversaries get to pick two messages, x0 and x1, and they send them over to Alice. And then Alice is just going to encrypt one of them at random. So which message she encrypts is dictated by this bit that she samples from 01. She encrypts that message and sends it to Clarence. And then the rest of the game proceeds as normal. And at the end, P1 and P2 just need to guess which of the two messages was encrypted. So equivalently, they just need to guess a bit. Ideally, we want this success probability to be at most a half plus negligible. That's the ideal security notion. This is what we'd ideally want. And this is kind of what the difficult open problem is, as I'll explain. So first, okay, let me tell you why it's still interesting to study search security. So ideally, you would want indistinguishable security, but how could you plausibly bootstrap from search to insecurity? So let's assume we have a scheme, which I'm going to call search enc, that satisfies search security, which is the first notion I introduced. Then there's this very simple transformation, which I'm going to call indenc, which will sample a string r from 01 to the n, and it outputs a state which is going to have two components. So one is, it's kind of like a pseudo-random one-time pad. So you one-time pad x with a pseudo-random function applied to r. And then, in a pseudo-random one-time pad, you'd normally send r in the clear. Instead, I'm going to encrypt it under this search secure encryption scheme to kind of get the unclonability guarantee. And I want to stress that we don't have security proofs for this. This is just like a plausible reason why you should still care about search security. And in particular, Broadbent and Lord provided some mild evidence that this might be indistinguishable secure when the PRF's instantiated with a random oracle. And I want to emphasize that actually proving indistinguishable security of any scheme is a notoriously difficult open problem. That's what Justin mentioned earlier. And there's a super important and exciting line of work. And I think most recently, Justin, correct me if I'm wrong, but most recently there's a work by Anand, Kalioglu, and Yuan, where they basically come up with the first indistinguishable secure scheme, albeit with the caveat that they need quantum decryption keys. Okay, so all of this is just to say indistinguishable security is an open problem. It's very difficult, but search security is still an interesting problem. I'm going to convince you in the...
Figure out why it's hard. No, sorry. I'm just trying to figure out why this is hard. Like, it seems like this is like, of course this works. Why would this not work, you know?
Um, Good. So the one sentence answer is that like to prove any kind of reduction like this, you need some kind of you need to prove something like Goldreich-Levin in this setting because like you need some kind of search to decision reduction, right? Um, because you need a search to decision reduction, and the way you would do that is with something like Goldreich-Levin. Except you have this annoying additional like constraint that's somehow important that there's two different parties and they don't get to talk to each other. And it's just that like, the technicalities of like proving the variant of Goldreich-Levin that you would need seems very difficult.
Yeah,
Like it is a cleanly stated conjecture in some paper. We just don't know how to prove it.
Yeah. What do you
yeah, to
suggest?
add a little bit more on that, the
Yeah, go
issue
for it, Justin. Yeah, please.
on each side, each extractor, if we just apply basic Goldreich-Levin, seems to need to operate independently. But if you operate independently, then you completely lose the fact that the two prover or the two adversaries are only guaranteed to succeed if they get the same key.
Hmm.
Run Goldreich-Levin, you essentially have to give them different keys.
Not sure I follow that, but maybe we should go.
Yeah, we
should
can
go
focus on
like, I mean,
this.
to me, it just seems like maybe like an indistinguished, like kind of a hybrid argument where you like, replace the search encryption with like some other R prime because like, how would you tell the difference? And, I mean, of course, it's hard because people have
Yeah.
thought about it. Yeah, okay, sounds good. Yeah, we can move on.
Yeah. Yeah, I think yeah, it takes some staring at it to appreciate why it's hard. But yeah, so I'm going to focus on search security for this talk. This is just kind of a justification that it's still interesting. Okay, so we're actually going to consider a slightly kind of more general notion, which is multi-copy search security. So the game now is that instead of sending one ciphertext state to Clarence, Alice is going to generate T identical ciphertext states where T is allowed to be any poly in lambda. And she's going to send all of these copies to Clarence. And now Clarence's task is to forward something onto T+1 players. So, you can think of the original game I showed you as the case where T equals 1. And now the goal is exactly the same. You just want all T+1 players to guess X correctly. And as Matan said, like, as we're going to see, it's going to be easy to get T players to guess X. The challenge is just getting that last player to guess X as well. That's kind of where the challenge lies.
Is it
Yeah.
encryption of the same? Is this just like the same encryption, or is this
No,
different?
the same encryption, like think like same hidden randomness, everything, if you're going to include hidden randomness.
Okay.
Yeah. Um, okay, good. Okay, so now let's kind of just lay out a trivial strategy for intuition, which I think Matan's already touched on. And this is going to attain a success probability of 2 to the minus n. So it's really simple. So Clarence has T ciphertexts. So he's just going to forward one ciphertext to each of the first T players. And now the first T players, they're good. Once they get theta, they're going to be able to decrypt and recover X. So they're going to guess correctly. But poor PT+1 has absolutely no information, so the best thing that they can do is guess xt+1 randomly. And the success probability of this strategy is 2 to the minus n. So ideally, our goal would be to come up with a game which doesn't admit any strategies achieving better than 2 to the minus n. Okay, so with that, I will keep going. All right, so for those of you in the audience, so I do want this talk to be as kind of classical friendly as possible, so I just wanted to lay out some Quantum 101 for some intuition before diving into previous work. So, in the classical world, a bit is kind of our atom of information, and that just stores a 0 or 1. But in the quantum world, the analog of a qubit is, you have your 0 and your 1, but which I denote with which I'm kind of wrapping these funky brackets around. But what I'm also going to allow you to do is to take linear combinations of them. So a times 0 plus b times 1 for like complex numbers a and b. And kind of the thing that you get access to is you get the ability to distinguish between orthogonal states. So one example is in the standard basis is what we call. So this is where you just take 0 and 1. And what is the basis? Like, what do I mean by orthogonality? I'm just going to identify these qubits with vectors by just kind of listing out the amplitudes that they place on 0 and 1. So the 0 state corresponds to a vector 1, 0. The 1 state corresponds to a vector 0, 1. These are clearly orthogonal, so we can distinguish them perfectly. Example 2 is called the Hadamard basis, which will come up a good amount in this talk. So you can think of this as two states, which are sometimes denoted by plus and minus, but you can think of them as one state is 0 plus 1, one state is 0 minus 1. And if you interpret these as vectors, the first one is 1 comma 1, right? Because that's the coefficients in front. The second one is 1 comma minus 1. Once again, these are orthogonal, can perfectly distinguish. And the one idea that kind of underlies a lot of these approaches to unclonable crypto is that when you want to encode a classical bit in a quantum state, you get a lot of freedom in choosing what basis you do that in. I could encode it in the 0-1 basis, or I could encode it in the plus-minus basis. And the point is that if you don't know what basis it's in, it's hard to recover the encoded classical bit with non-trivial probability. And it's also hard to clone without knowing the underlying basis. So kind of the fact that we can hide bits behind this choice of basis is kind of what buys us unclonability, and that's going to be a theme throughout the talk. So I'll pause there to see if there are questions. Okay, in that case, I'll move right along. Okay, so now I want to tell you a bit about previous candidates for unclonable encryption and what about them that I think leaves something to be desired. So the first candidate I want to talk about is based on BB84 states. So the idea here is Alice is going to sample a key that's also n bits long. And she's going to basically she's going to do exactly what I hinted at in the previous slide. For every bit of X, she's going to randomly decide whether she encodes that in the standard basis or the Hadamard basis. And this choice is what she writes down in theta. And then she just goes ahead and does that. If it's, if a bit of theta is 0, she encodes that bit of X in the standard basis. If a certain bit of theta is 1, she encodes that bit in the Hadamard basis. And another way to write this is h to the theta applied to x, the expression on the very right, where h stands for a Hadamard gate. And then your ciphertext state, we also kind of informally denote it as x to the theta, which you can think of as x encoded in basis theta. Okay, and previous work basically shows that in the t equals 1 case, the value of this game is like a cos squared pi over 8 to the power of n. So it does exponentially decay in n, but the constant in the top is not ideal. We'd ideally want 2 to the minus n. But it turns out this is tight as well. There exists a strategy achieving this. And for those of you who've seen this constant somewhere and are feeling some weird deja vu, the other place where you may have seen it is the CHSH game, and it shows up for much the same reasons. That's just a side remark. You don't need to understand that. Okay, good. And now what I'd like to emphasize is that as soon as T is even 2, as soon as Clarence gets 2 copies and has to forward to 3 players, it's completely broken. There's actually a way that, these adversaries can guarantee that they win. And how's this going to work? So what Clarence is going to do is he's going to take one copy and measure it in the standard basis, as if theta is all zeros. And he's going to take the other copy and measure it in the Hadamard basis, as if it's all ones. And then all he has to do is he's just going to forward all these results to the players. And the players later are going to find out theta, so they know what the correct basis is. And now what they can do is they can basically mix and match Clarence's results to recover the message perfectly. So all of them output X correctly, and that's it, game over. Okay, so any questions about any questions about this kind of BB84 approach being broken for T greater than 2?
So just like non-quantum question. So if Alice like encoded things, say in the Hadamard basis, and I measure them in the standard basis, would I just get like the same result, or like?
You get a random bit, so that's what we're using. So if
Okay.
if you look at it in the wrong basis, you'll get 0 or 1 with equal probability.
Okay, that makes sense.
Yeah, good question. Any other questions?
Sure. So if we took maybe a higher dimensional basis where we could have more than 2 of these, but they're in some sense mutually unbiased. And what I mean by this is if you consider the state in one basis, you measure, or you consider a basis state for one basis and you measure it in a different basis, you get uniformly random results.
Sure.
Yeah, if you had many of these, could we say get as many copies as you had bases?
Yeah, I think this is Yeah, it's a good question. I think this is plausibly true. Like, I don't know how to break it. I also don't know if it's been analyzed.
Fair
Uh,
enough.
but yeah, but it's a good question.
So
Uh,
would these bases be over more than one qubit to make this happen? Okay.
Yeah.
Um, I think you could conceivably do it with one qubit, right? Like you could imagine having like you can kind of think of the kind of standard and Hadamard basis as being bases that are like a 45-degree angle apart, and instead you could take like three bases that are like 30 degrees apart each, and like
That's an interesting question, because I know that if you want them to be completely unbiased, then there's a cap in how many bases you can get. So for example, if you
yeah.
took basis 0 plus I1 and 0 minus I1, this is also mutually unbiased with both the Hadamard and the computational basis.
Mhm.
But you can only get 3 of these. I think it's something like
I see.
n plus 1, where n is the number of qubits.
I see. I see. Huh, interesting.
Yeah, that's sort of what I was thinking, but there would be a cap in n, right? So
Yeah.
you're needing to expand the bases. I mean, that already gives you something, maybe.
Yeah, it's an interesting question if you could get away with making them not entirely unbiased.
Yeah.
Okay, cool.
Yeah.
In that case, oh, sorry.
No, you just
No,
said sorry.
I-
Yeah, you keep going.
Oh, okay, sure. Yeah, I will move on to another candidate, which is another thing that often appears in unclonable cryptography, which is subspace coset states. So let me unpack what that means. So the key, I'm not going to think of it as a bit string for convenience. What I'm going to think of it as is a subspace, a linear subspace of f2 to the n, of dimension n over 2. So Alice samples this key, and then the way she encrypts is that she takes a message and passes it as two cosets. So one is a coset of A, which has dimension n over 2, so there's n over 2 bits of information there. And the second one is a coset of A perp, the orthogonal complement of A. And this is some other S prime, and this has n over 2 bits of information. So you can certainly pass a message in this way.
So what's this S?
Um, think of S as just like an arbitrary element of f2 to the n. So what you should think of is that like by coset, what I mean is that I want to say that like two S's are equivalent if they differ by something in A.
Okay.
And then I'm like sampling an equivalence class.
Okay. Sounds good.
Um, so now like, and you should imagine that there's like some canonical way to take an X and like compute an S and S prime corresponding to it.
Okay.
So then once you do that, you can define this state A that depends on X or equivalently S and S prime, which is a superposition over every vector in A, except I'm going to shift it by S. So in other words, it's a superposition over the coset A plus S. And then in addition, there's one more twist. I'm going to apply a plus or minus one amplitude to each of these terms. And whether I apply a plus or minus one amplitude is determined by the inner product of S prime with A. So in particular, whether it's 0 or 1, mod 2. So this is another type of object that's come up a lot in unclonable cryptography. And previous work, again, it analyzes the t equals 1 case, and they show that the value of this game is still exponentially decaying in n. This bound, we don't know if it's tight. But we have some exponentially decaying bound in n. Still not the ideal constant, but okay, maybe that's fine. And I'd like to claim that once your number of copies is much bigger than n, this is completely broken. And the attack kind of proceeds very similarly. So all Clarence is going to do is he's going to take about half the copies, measure them all in the standard basis, and measure half the remaining half of the copies in the Hadamard basis, and forward these results to all the players. And what you should imagine is that like the first copy kind of basically tells you what S is, and the second copy basically tells you what S prime is. And the players also get a description of A, so it's even easier, and they can use these results to output S and S prime. So once again, completely broken when t is much bigger than n. So if we care about multi-copy security, the kind of existing state of the art leaves a bit to be desired. Okay, so I threw a lot of maths at you. So any questions about the coset states construction?
It seems like you would only need 4 copies, right? Not many, because you measure 2 in the computational basis, 2 in the Hadamard basis.
Uh-huh.
And then you just subtract the 2 computational basis ones from each other to get an S. You subtract the 2 Hadamard basis ones from each other to get, or no, an A.
So if you say, so I think that works as a distinguishing attack, but if you want to actually decrypt, I'm not sure if that would do the job.
Ah, okay, okay, makes sense.
Yeah. Yeah, good. Other questions? Okay, in that case, I will move along. And okay, so hopefully I've convinced you that it's, multi-copy security is a hard thing to get. It's a difficult problem. And we thought about kind of solving it in this kind of the same model that the BB84 and the coset states are analyzed in. But we couldn't do it, so instead we settled for like a simplifying assumption. And what we're going to do is instead of giving each of the parties direct access to the data, what we're going to give them is Oracle access to a decryptor. So there's some Oracle in the sky that decrypts with respect to key data, and we give them one query to this Oracle. And on the one hand, this is quite an aggressive restriction. But I'll make two remarks. So one is that, unclonable encryption is a pretty difficult problem, and, similar Oracle models, albeit less aggressive, have been used in other works. And this still enables the trivial 2 to the minus n strategy that I mentioned earlier. Because if Clarence just forwards an honest ciphertext to a player, they can just query the decryption oracle to recover the message X. So we're still kind of in the same game of like wanting to beat 2 to the minus n. So this is, yeah.
All the previous schemes that you showed are insecure in this model?
Um, it's a good question, and the answer is that I don't know off the top of my head. Um, I think the fact that you have an oracle, um, let me think. Yeah, I think it's still insecure for enough copies because like maybe not using the attacks that I mentioned, but like once you have enough copies, you can literally learn exactly what the state is, in both cases.
Okay.
Like you might need more copies than what I claimed for the attacks on the previous slide, but
Is it poly copies or is it exponential?
no, poly, like just a large poly, many copies.
Okay.
And like those attacks, like they wouldn't even need to use these oracles to run them.
Okay.
Yeah, I think that's true. Um, because okay, like here's the attack for the BB84 case. Like Clarence will just measure like 100 copies in the standard basis and 100 copies in the Hadamard basis. And at this point, like he'll have a pretty good guess for like what the right basis is for each position. And then like he can just kind of tell the players what the message is. Yeah, so actually like this oracle is not even needed, perhaps to break these previous cases. You just might need more copies than what I presented.
Okay.
Good question. Other questions? Okay, cool. In that case, I will move along. And let me kind of state our results. So we kind of present the first candidate unclonable encryption scheme, which is plausibly multi-copy search secure for any polynomial number of copies. And we provide like, a first step or some mild evidence towards this scheme's security. And what we do is we provide a proof when t is much less than n over log n in the single oracle query model. And I want to mention that, this result, it's worth taking this with a grain of salt because like you need more than n copies to break the subspace coset states. So this isn't like clearly putting this scheme above the coset states construction, but there are some good reasons, which I'll explain later, to kind of believe that this scheme is truly multi-copy secure. So we're hoping that our techniques can be extended past this. And in fact, when t is constant, we actually literally prove the success probability of order 2 to the minus n. So this is essentially tied down to constant factors, like we get the right constant in the exponent. And, previous work did show how to do this for t equals 1, with the caveat that the ciphertext states have to be large. They have to expand the n qubits to like, something like 2n or 3n qubits. We don't need this. We only need n qubits. And you might think that these distinctions are kind of arbitrary, like why would you care in the crypto world? So it turns out that we actually need both of these properties of our scheme to kind of connect our result through to black hole physics later in the talk. And this kind of relies on these two properties of our scheme. So that's a statement of our results. Let me pause here and see if there are questions. And if not, I can kind of get into it. Okay, in that case, I will move along. Okay, so what's our construction and analysis? So I think for some inspiration, I'm going to take a detour to talk about quantum pseudo-randomness. So, for every notion of randomness and pseudo-randomness in the classical world, we've kind of come up with a nice quantum analog for it. So, in the classical case where you have a random n-bit string, in the quantum case, we have a nice notion of what it means for an n-qubit state to be uniformly random. We call it the Ha-random n-qubit state, and never mind what that means. Um, then you also have a classical notion of pseudo-randomness, right? You have a PRG, you have something that generates n-bit strings that looks random. You could correspondingly think about pseudo-random states, something that takes in a short classical seed as input and outputs some n-qubit state that looks pseudo-random. And you can play the same game with functions, right? So if you have a random function on n bits, this is something like a Ha-random unitary on n qubits. Once again, there are pseudo-random notions. So pseudo-random function, pseudo-random unitary. And the two quantum notions here that we'll be using in this talk are pseudo-random states and Ha-random unitaries. And for kind of the immediate future, I'm going to be talking about pseudo-random states. I'll talk about Ha-random unitaries later in the talk when we get to the black holes. Okay. So with that, I will move along. So let me actually formally define pseudo-random states, since we're going to make use of that. So you should think of it as being a function which maps a lambda bit classical string to an n-qubit state. And the security guarantee is kind of what you expect. So in the ideal case, if I sample a state psi, completely random on n qubits from the Ha measure, and send you t copies of it, this should be indistinguishable from if instead I sample a seed k, feed that into my pseudo-random state generator, and then send you t copies of that. So that's what we want from a pseudo-random state. And it turns out that pseudo-random states enjoy unclonability properties, which is kind of our reason for kind of trying to bring them into the unclonable crypto world. So Werner showed that Ha-random states are multi-copy unclonable. So it follows just by a straightforward hybrid argument that pseudo-random states are also multi-copy unclonable, which makes them a natural candidate for unclonable encryption. So I'll pause here again and see if there are questions. Okay, excellent. In that case, I will move along. And let me tell you a bit about one construction that we have of pseudo-random states. So this is due to Ji Liu Song in 2018 and Brzezinski and Shmuley in the following year. And the theorem is basically that if you have post-quantum PRFs, then you can construct pseudo-random states. And what does the construction look like? So let's use f sub k to denote my PRF from n bits to 1 bit. And then my pseudo-random state is going to take a uniform superposition over all n-bit strings. And on each of them, it's going to place a plus or minus 1 amplitude. And it's going to do that pseudo-randomly. And the way it does that is it just feeds z into the PRF. And then if you get a 0, you don't do anything. If you get a 1, you apply a minus 1 in the phase. So it's kind of this like plus minus 1 superposition over all these kind of individual basis states. So that's the construction. And one alternate way of writing this is so exactly what I said. So you start off with this summation over z, and then to the left of it, you apply a u sub fk. And what is u sub fk? It's just basically an oracle. You can think of it as an oracle for f. So it takes in a classical string z and applies a phase according to whether f of z is 0 or 1. So in those terms, like you can write this pseudo-random state as u sub fk, u sub fk, then a Hadamard, and all of this is applied to the all zeros string. So this is kind of the construction of pseudo-random states that I'm going to work with. So I'll pause here for questions.
What do you mean phase oracle? Like, sorry.
Good. No. It's a good question. So in the quantum world, it's not completely trivial to figure out what the right way to represent an oracle for a function is, for a classical function. And the reason is that like quantum unitaries need to be reversible. Like, how do you represent a non-injective function? So what a phase oracle does is it takes a string, so it takes a superposition over inputs. So it's some state that can be in superposition over its inputs. But then, okay, you know what? Let me not even do that. This phase oracle basically takes a classical string as input. And by phase oracle, what I mean is, if f of z is 0, it leaves it as is. And if f of z is 1, it just flips the sign. It sends it to minus z.
Okay.
It's kind of like implicitly writing down the function by like flipping the sign in front of z.
Okay, now maybe see, yeah, that makes sense.
Yeah. So phase in this talk refers to like that amplitude, like plus or minus 1.
Okay.
Good. More questions. Okay, in that case, I'll keep moving. So let me kind of give you our unclonable encryption scheme from pseudo-random states. So our inspiration is going to come from like, just baby, one-time secret key encryption using a PRG. So if I want to encrypt M under a shorter secret key K, what am I going to do? I apply a PRG to K, and then I just use that as a one-time pad for M. So, all we're going to do morally is just take this construction, but it's just switch out the PRG for a PRS. That's the name of the game. And it's exactly this. So that's what I've written on the left. So you take gen of K, which is my pseudo-random state, and then I hit it on the left with Z to the X, which you can think of as basically encoding X in the phase. Encoding X in the phase. So now what you get is some superposition over all bit string Z, except now the phase or the amplitude depends on two things. It depends both on the pseudo-random function applied to Z, as well as the inner product of Z with X. And so another way to write this is, a Hadamard gate applied to X, followed by this phase oracle, U for F. So that's our construction. And for decryption, all you need to do is undo these two operations. So first, you can undo the phase oracle just by applying it again, since it's plus or minus 1. And then you can undo the Hadamard with another Hadamard, and then you just get X. So that's decryption. So let me stop here and see if there are questions about the encryption scheme. Okay, I will keep going then. And thanks to Werner, we know that these states aren't multi-copy clonable by a computationally bounded adversary. This is just because they're indistinguishable from random. But once again, this is not good enough for us, right? The goal is to prove a stronger theorem that is useful no cloning. And so what we'd like to show is that, cloning Clarence can't construct any t+1 states that reveal X given K. And it's because of the difficulty of proving the stronger claim that we go to an oracle model. Okay, so with that, let me kind of say a few words about how the proof goes. I'm probably going to skip over a lot of it.
Yeah, sorry. Good question.
Could I ask, what is the difference between the two claims that you just?
Good. But okay, good. Okay, so what I mean is, so multi-copy clonable means like I give you an encryption of X, and you just take that state and exactly make like an extra copy of it. So I give you one copy of a ciphertext, you give me two copies of the exact same ciphertext. But the stronger version is a different task. In the stronger case, what I want is like, Clarence doesn't necessarily have to produce two copies of that exact same ciphertext. It just has to be like two things that reveal X. Like Clarence is free to like, if he can recover X, he can just write down X on a sheet of paper and send it to the two players. So the point is that Clarence has a lot more freedom because the only goal is to recover X. He doesn't have to replicate the ciphertext exactly. Does that make sense?
Yeah.
So I think another thing here is that like the secret, like just the classical scheme as you described it, is only usable once, right? Since you're using like PRG on K.
Yeah, good. So even the quantum scheme here is only usable once.
Okay.
But like if you want to boost it to like an actual scheme, you would kind of go through the transformation I said, like with the PRF and the like pseudo-random one-time pad.
Okay.
Yeah, so we're kind of, I guess for this to be a cryptographically interesting thing, you'd want to push it through like that transformation.
Which I guess we don't know if it like works, right? We can't prove it.
Yeah. We believe it works, but I don't have like proofs for it. Yeah. So yeah, I think, this field is littered with open questions and like there's plenty to be desired still, I think. Okay, excellent. Other questions? Okay, great. Okay, so let me just say a couple words about the analysis then, and then at some point I'll kind of just abort and cut across to saying a couple of things about black holes. So this is kind of the same security game. I've just kind of rearranged things to kind of buy myself some real estate. So, the first step is kind of a straightforward hybrid thing. Instead of a PRF, I just want to kind of migrate to a truly random function F. So that's the first thing I'm going to do. And here we need the players to be computationally bounded, since we're relying on PRF security. But after this point, we don't need any computational boundedness. Like everything's information theoretic, albeit with the significant restriction that P1 and P2 only get to make one query. Okay, so with that, I will keep going. Okay, so now f sub k is just f. It's a truly random function from n bits to 1 bit. And the second step is to kind of switch to what is called an entanglement-based formulation, which is where Alice never actually sends anything to Clarence. Instead, what we're going to do is Alice and Clarence begin the game sharing what we call entangled qubits, and then Alice just has to do something on her side to kind of teleport. You can think of this as being like quantum teleportation. She just does something on her side to teleport a state over to Clarence. So these kind of squiggles is this like entanglement shared between Alice and Clarence. And then Alice is just going to, so we're also going to reorder the steps of the game. So Clarence starts by acting arbitrarily on his half of the EPR pair, and he forwards whatever he wants to P1 and P2. Now we can forget about Clarence. Clarence isn't in the game anymore. Now Alice samples a function and applies some measurement on her side. And what this does is it has the effect of saying, okay, well, Clarence might as well have had, you know, a ciphertext state in the beginning. And then the game's the same. P1 and P2 make one query to U sub f, and their winning condition is if the two of them and Alice all got the same measurement probability, got the same outcome. And this is known as a monogamy of entanglement game. And this is a very commonly used tool in unclonable cryptography. And the existing kind of suite of techniques we have for analyzing monogamy games face two problems. So one is that they can only ever hope to prove an upper bound of 2 to the minus n over 2 on winning probability. And ideally, we'd like to shoot for 2 to the minus n. And you can see our paper for a proof explaining why. And the second thing is that it also provably can't establish any meaningful bound in the multi-copy case. Like this is really something that's specialized to the 1 to 2 case. Whereas we would like techniques that kind of get around both these problems. So this is kind of why we introduced the new tools in our paper that we do. Okay, so I'll stop there and see if there are questions. I think that's a good pausing point. Okay. In that case, I will soldier on. And now we just kind of roll up our sleeves and calculate. And the nice thing is that because of this single query assumption, it's actually kind of easy to get our hands on an expression for what comes out of this game. And what we're going to assume is that P1 and P2 proceed as follows. They start by making a query to this oracle for f, then they apply some unitary, and then they measure in the standard basis. And now it's easy to write down the probability that basically all three parties output the same x. And it's basically this expression. So what you should think of this as is like an overlap. So on the left, you have the state that the three parties share after Clarence is done doing his thing. And then on the right, what you have is kind of the state that you would ideally want all three parties to have if they were to all output x. And the probability that you have one state but measure another is their inner product squared. Okay, good. So let me keep going. So the goal is basically to upper bound this thing. And we're just going to unwrap this a little bit more. So another technique that's often used in these analyses is to basically say, I'm going to throw away the state psi. And I'm just going to say, at the end of the day, this is, psi dagger times some matrix times psi. And I can always upper bound this by the largest eigenvalue of the matrix in the middle. So what we do is we take this matrix in the middle, and what other works have done, we take this matrix in the middle, and we want to upper bound its spectral norm. And we want to bound the spectral norm of this. And now the observation we're going to benefit from is that these U sub f's kind of live on the outside. So we can really pull them out. And so we just, sorry, yep, question.
Yeah, go ahead.
The U's are unitary, or are they? Oh, you're treating them as an oracle. Okay.
Yeah, they're phase oracles. Yeah.
Question rescinded.
No, thanks. Yeah.
Spectral norm less than 1 now.
Yeah, I mean, you'd like spectral norm less than 2 to the minus n, I think.
Right. Yeah, for a moment I was thinking that the U's were unitary, in which case it doesn't change the norm, but because they're oracles, that makes sense. Why it would decrease the norm.
Yeah, exactly. Yeah, that's exactly right. Yeah, so we'd like to bound this spectral norm, and there's some ugly, matrix in the middle. Let's not worry about it. I'm just gonna call that chi. And what you want to do is you want to bound some expression of the form UF, like you want to bound some expression of the form expectation of UF tensor 3 times chi times UF tensor 3 times. And maybe let me just give you a nugget of how we analyze it. So we have some expression. And what does this expectation come out to be? So if you think about it, I can index rows and columns so a row is indexed by x1, x2, x3, where each of these is an n-bit string. And likewise, columns are indexed by y1, y2, y3. And its entry is just going to be you take out the corresponding entry of chi, but then you have an expectation over functions f of -1 to the power of this sum over evaluations of f. And the observation is that this is going to be 0 most of the time. In particular, if some string appears an even number of times out of these 6 entries, appears an odd number of times out of these 6 entries, then, f is a random function. So the contribution from that will be plus or minus 1 with equal probability. And then you'll get cancellation. So this term will vanish. So this is exactly what I'm saying at the end of this bullet point. If some string appears in this collection of 6 an odd number of times, then it comes out to 0. If every string appears an even number of times, then the expectation is 1. And, I think maybe let me skip the technicalities and let me just show you a picture of what's really happening here. What this basically is going to do is it takes this matrix chi, which is this 4x4 block matrix, and it basically clusters, collections of 3 strings into equivalence classes according to like which strings appear an odd number of times.
Sorry, where's this number 4 coming from?
It's arbitrary. That's just for the purposes of the diagram. There's going to be many more than 4 in general.
N?
Sorry?
Is it supposed to be n? Is 4 like equals to n and you're just fixing for the sake of
No,
it?
4 is like going to be like exponential in n. Like 4 is like a very big number.
Okay.
This is just for visualization purposes.
The n, it's like overall possible states.
Yeah,
Okay.
exactly. So this is so basically what you should imagine is that kind of applying this kind of transformation, which is called a twirl, is taking this matrix chi, but then it's zeroing everything out except stuff that's on the block diagonal. So then if you want to bound the spectral norm of this matrix, all I need to do is look at one of these blocks and show that that block has a small spectral norm. And this is kind of what we do. Let me not kind of dive into technicalities of how we go about doing it. But that's kind of a terse sketch of how we prove our results. So let me skip this. You know what? Maybe let me leave you all with a linear algebraic lemma that, it's something, as far as I know, excuse me, as far as I know, a new thing. And we had to prove it for this work, and let me just state it in case it's useful for some completely unrelated reason. It shouldn't be obvious at all why this lemma is useful, but let me state it anyway. So let A and B be these gigantic block matrices. So there's R row blocks and R column blocks. And let's say that each of them has spectral norm at most 1. And then what I'm going to do is I'm going to come up with an even bigger block matrix, where in each block, I take the tensor or Kronecker product of the corresponding blocks of A and B. And in addition, I apply a rescaling in each of these blocks by some gamma that's a complex number of magnitude at most 1. And what we show is that, no matter what A, B, and gamma you choose, this final matrix you get also has spectral norm at most 1. And this is kind of the main kind of technical thing that we end up having to prove to show our results. Okay, since this is kind of a standalone result, let me just kind of stop and see if there are questions about it.
Yeah, so this final matrix is something like E tensor to A tensor B?
No, so A tensor B, so if you forget about the gammas, this thing is a submatrix of A tensor B.
Oh, it's a submatrix of A tensor B, okay.
Yeah. So in particular, like if the gammas weren't there, this is easy to show, right? Because this is a submatrix of A tensor B. A tensor B has spectral norm at most 1. So then you're done. But the gammas turn out to make things quite a lot harder to deal with.
Makes sense.
Yeah.
I missed
Yeah, good question.
was there, but okay, that's interesting.
Okay.
Any other questions about
No, but just how long do you think you have? I mean, we started late, so it's our fault.
No,
But
no, that's okay. I was going to cut across to the black holes and just give a brief spiel on that, which should hopefully be high level and not super technical, and then I'll stop. So maybe like 10 minutes, is that okay?
can we do 5 minutes?
Yeah, yeah, done. We can do 5.
Thanks.
Okay, thanks. All right, so let me skip the summary about construction and let's get into some physics. And some of these slides are thanks to Alex. Um, okay, so let me start with a very simple view of black holes, which is what I had in mind before this project, and it turns out to be wrong. So basically, black holes are just some kind of giant mass. Whatever you throw in never comes out. And Hawking in the 70s kind of proposed that maybe there's a more nuanced thing happening. And black holes aren't completely black, they slowly emit radiation. And so what this means is that over time, black holes actually completely evaporate. So initially it's pretty big, it's emitting radiation, then it gets a little smaller, still radiating, even smaller, and then finally it's just gone. Everything in there is radiation. Sorry, everything's come out as radiation. So the question that kind of we think about and has been thought about before is if I, throw a classical message into a black hole, like I write something on a piece of paper, what happens to it over time? And for small t, then there hasn't been much or any radiation yet, so it's entirely inside the black hole. And for large t, the black hole has evaporated completely, so it must be hidden in the outgoing Hawking radiation. And, this is something that's been considered before. There are previous thought experiments that basically say that, once it's evaporated, the information might be hidden in the outgoing Hawking radiation. But they provide some evidence based on thought experiments that it might be computationally hard to decode the Hawking radiation.
We think like it's hidden in there because we think it's hidden in there because like, all quantum stumping is reversible, so information should be conserved or something like that, or is otherwise why isn't it just like squished forever, right?
Yeah, it could plausibly be destroyed. I'm not familiar enough with the black hole physics to like
Okay.
understand why people believe that it doesn't get destroyed. But
Okay.
yeah. Yeah, I should kind of hedge all of this with like, I'm not a black hole physicist. Like, I'm not even I've thought about it for a while with Alex, but I'm not even the person who originally made this connection. That was Alex. So kind of what I can say about this is limited, but I'm kind of trying to provide some picture. Okay, and then there's also this recent work of Brzezinski that kind of connects the computational hardness of decoding Hawking radiation in some specific models with the existence of secure quantum cryptography. So that's kind of the landscape. So that's small t and large t. And what I think of our work as doing is like, what happens for intermediate t? Could there ever be a point in time where we kind of interpolate between these two regimes? Could there be a point in time where the information is recoverable both inside and outside the black hole? And if you think about this a little bit, this actually looks a lot like an unclonable encryption game. Because what you could imagine is that Alice throws a random classical k-bit message into the black hole, which has like some n minus k qubits. And then you let the black hole evolve in 2 steps. So one, some hard random unitary is applied, which you can think of as kind of just completely scrambling what's inside the black hole, which is kind of a modeling assumption that physicists tend to use. And then there's some like Hawking radiation channel that arbitrarily splits this into a final interior state for the black hole and radiation R. And now it's actually a very similar cloning game because there's a player 1 inside the black hole and a player 2 outside the black hole who's kind of receiving the radiation. And the kind of natural model in our setting is that they each get one oracle query to U or U dagger, which you can think of as kind of having like some superhuman knowledge of physics. And they know exactly how the black hole evolved over time, so maybe they can somehow reverse it. So we give them one query to U or U dagger. And now they both output their guesses for X. So it's a very similar setting to the unclonable crypto game. And basically what we show is that under these modeling assumptions, the probability that both parties can recover X is order of 2 to the minus K. And this is fairly immediate after showing our unclonable encryption result. And maybe the new idea is that, how do you account for this hard random unitary? You kind of view the hard random unitary as like as an alternate way of encrypting. And thanks to the Haar measure being kind of uniformly random, you can apply some worst case to average case reduction to just layer this on top of the encryption scheme that we have. So that's a very terse sketch of what we have to say about black holes.
This is reading like the phase thing with the PRF as being like computationally indistinguishable from hard random unitary. Is that the idea?
No, so that is not true. But what I'm going to do is I'm going to take the phase oracle, and then I'm going to pad it afterwards with a hard random unitary. Because like why not? Like I can take a ciphertext and then just apply a hard random unitary to it. And now the thing you're using is that if you take this particular PRF operation, then apply a hard random unitary, that's the same as if you just had a hard random unitary in the first place. So this is what I mean by worst case to average case reduction. You're kind of re-randomizing the encryption unitary.
Okay.
All right, let me quickly close with open questions. So I think our results for search security leave a lot to be desired. There's a technical challenge, which is like, can you get away with more queries? And there's a conceptual challenge, which is like, what if we just send all the players the secret key in the clear, rather than kind of providing this decryption oracle? So it's kind of weird because we're throwing PRF security out the window now by leaking the secret key. But at the same time, we are able to prove guarantees for BB84 and coset states in this kind of bizarre model. So that's kind of a conceptual challenge, I think, that requires completely new ideas. And the second thing is, again, this really important question, this ideal notion of indistinguishable security with classical decryption keys, plain model, no random oracles, nothing. And this is open even for t equals 1. And lastly, we make some idealized modeling assumptions in the black hole radiation decoding stuff. Like, we talked with some physicists and they seem pretty happy about it and even excited. But we can always make the model more general. I think it's interesting to continue exploring these connections between, black holes and quantum crypto. So with that, I'll stop. Thanks very much.